Section 2.8. The derivative is a function. Previously, we saw a definition for the derivative at a point A, given as f prime of A. Now we'll consider the derivative as a function of x in general, where pretty much the same definition applies, where we say that f prime of x is the limit of f of x plus h minus f of x over h as h goes to 0, provided this limit exists. Remember that this is the exact same thing as the limit as x goes to a of f of x minus f of a over x minus a. So the graph of a function f is given. Let's use it to sketch the graph of the derivative f prime. Well, it looks like from the graph of f that if we have a tangent line over here, it must have slope 0 because it'll be horizontal. If we have a tangent line over here, it must also have slope 0. And tangent line over here must have slope 0. So since we can think of the derivative as the slope of the tangent line, the derivative must be equal to 0 at those 3 points. So if 1 is over here, it looks like the first slope of 0 is a little bit before 1, maybe halfway. And then the second one is a little bit before 2. And then the third one looks to be right on the third one, right over there. Okay, it looks like if we look at the way the graph is changing before the first tangent slope of 0, looks like it's going down. If we were to draw tangent lines, the tangent lines are also going down. So they have negative slopes. So that means that the value of the derivative, because we're viewing the derivative as a slope, is negative. So before the first 0, all of the y values for the derivative should be negative. So we should have all negative y values before the first 0. Then the function starts going up, it starts increasing. So the derivative should be positive for all the values before the next 0. So it should go up and then return to 0 somehow for all positive y values. And then it looks like after the 0 it goes down for quite a while. So our derivative should be negative and then return to 0, and then it's positive all the rest of the way, the slope. So we should be positive the rest of the way for our derivative. So this is a rough graph of the derivative. Okay, if f of x is x cubed minus x, let's find a formula for the derivative f prime of x. Well, we'll use our definition. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. We usually use this definition because it gives us only one thing in the denominator to cancel out. It'd be easier to cancel out a h usually than an x minus a, just because it's more cumbersome with the notation. However, different formulas have different advantages in different situations. So at this point, instead of writing x cubed minus x, we write x plus h cubed minus x plus h. So that's for f of x plus h. Then we subtract off f of x, which is x cubed minus x. Okay, if we expand everything, it looks a little bit messy, but it should work out in the end. We get x cubed plus 3x squared h plus 3x h squared plus h cubed minus x minus h minus x cubed plus x over h. And then we cancel out everything that we can. this h goes to 0, we get 3x squared h plus 3xh squared plus h cubed minus h over h. Okay, notice that there's an h in every one of these terms. So that means we can just factor out an h, divide by it. So cancel out our h. Remember that we're going near 0 but not equal to 0, so we have no issue with dividing by 0. Sorry, dividing by h, because we're not going to be dividing by 0. So we end up with 3x squared plus 3xh plus h squared minus 1. That's a polynomial, so we can use direct substitution to get 3x squared minus 1. We just plug in 0 for h. Okay, let's illustrate this formula by comparing the graphs of f and f prime. So if we pull out our handy dandy calculator emulator and go to y equals, we can plug in f was x cubed minus x, f prime was 3x squared minus 1. So the original function will be blue and our derivative will be red. Okay, let's zoom in a little more. Notice that we would expect, remember the original one's blue, we would expect that the derivative would be 0 around over here, because that's when the tangent line is horizontal at this value right over here. And it is. If we go underneath, we can see the derivative is 0 over there. Oops. Similarly, if we look over here, it looks like our tangent line should be horizontal again, and the derivative over there is 0. If we look to the left of the 0, then we can see that the function is going up from our original function. So the slope of the tangent line should be positive, which it is. The red part is positive until it hits the 0. Then it becomes negative, which is when my original function starts going down, because the slope of the tangent line is then down. Then the original function starts going up again, and the red function goes above the x-axis and becomes positive again. So it looks like this is a good comparison. See if I can grab that. It really shows that we have the right formula for our derivative when we can graph it and it's consistent among all those different values. If f of x is the square root of x, let's find the derivative of f. Let's also state the domain of f prime. So f prime of x is equal to our fun limit of f of x plus h minus f of x over h. We plug in, instead of square root of x, it becomes square root of x plus h. And then minus square root of x over h. Okay, so notice we have a radical in our numerator. We can't cancel out h right off the bat, so it makes sense that we probably want to try to do it by rationalizing. So we have square root of x plus h minus square root of x over h as before, but we can multiply the top and bottom by the conjugate for the numerator, square root of x plus h plus square root of x. And since we're multiplying on the top, we have to multiply on the bottom. Okay, when we do that, our numerator simplifies a little bit. It becomes x plus h minus x. Our denominator is a little bit of a mess. It becomes h times square root of x plus h plus square root of x. I'm not bothering to simplify the denominator because I want to be able to easily cancel out the h, so having it outside is nice. Okay, notice on the top, the numerator, I've got positive x and negative x, so those just cancel and leave us with h in the numerator. So I have h over h times square root of x plus h plus square root of x. Alright, so I divide top and bottom by h. I get that this is equal to the limit as h goes to 0 of 1 over square root of x plus h plus square root of x. Okay, it looks like if we plug in 0 now for our denominator, it will not be undefined. So we can pass through our limit. We get that this is equal to 1 over the square root of x plus the square root of x by just plugging in 0 for h. So that's 1 over 2 times the square root of x. Okay, for our domain of f prime, notice it's got a square root and it is a quotient, so we have to worry about our denominator a little bit. For square roots, 0 and any other number will work that's bigger than 0. However, because this is the denominator of a fraction, we cannot divide by 0. So our domain of f prime is a little bit smaller. We have to just consider numbers that are bigger than 0, not including 0. Notice the domain for our original function, the domain of f, for comparison, which they didn't ask us for, but it's just good to see, includes 0, because you could take the square root of 0. You just can't divide by it. So in general, the domain of f prime could be the same as the domain of f. It could be a little bit smaller than the domain of f, but it could never be bigger than the domain of f, because you can't really take a tangent line someplace if a function is not defined, so you definitely can't look at the slope of a tangent line that doesn't exist. For example 4, let's find f prime if f of x equals 1 minus x over 2 plus x. Same routine. We just look at our limit. So f of x plus h minus f of x over h. In this case, it becomes a little bit messy because of this rational function, but we can persevere. So instead of 1 minus x, it's 1 minus x plus h. Instead of 2 plus x, it's 2 plus x plus h. And we're going to subtract f of x, 1 minus x over 2 plus x, and divide by h. So then we can simplify this out a little bit. We find a common denominator for our two fractions in our numerator so that we can subtract them together. So in the numerator, we should get 1 minus x minus h times 2 plus x minus 1 minus x times 2 plus x plus h. And in our denominator, our common denominator, notice, is going to be this 2 plus x plus h times 2 plus x, but then we're dividing by h, so that gets multiplied through. So we end up with h times 2 plus x plus h times 2 plus x. Okay, so then this equals the limit. Well, notice in the numerator, tons of stuff cancels now. We just end up with a minus 3h. And our denominator stays a little bit messy. Okay, so now we have an h that we can cancel on top and bottom. We divide top and bottom by h, which is wonderful, which will eliminate the possibility of an undefined denominator at 0. So we'll be able to evaluate it there. Okay, so then we plug in 0 for h, and we get that this is equal to negative 3 over 2 plus x squared. In general, the symbols d and d over dx are called differentiation operators and are used as follows. F prime of x is equal to y prime, which is the same thing as the limit of delta y over delta x, the change in y over change in x as delta x goes to 0, which is the same thing as dy dx, which is the same thing as df dx, which is the same thing as ddx of f of x, which is the same thing as df of x, which is the same thing as dx f of x. So we have a million different ways to talk about differentiation operators. They all mean the same thing, just take the derivative. And they have different contexts and uses depending on what's going to be most handy in the situation. Most of the time, we'll be using this one, or this one, or this one, maybe this one, depends on the situation. We probably won't usually use the last two. For fixed a, we use the notation dy dx evaluated at x equals a, and we either use this line or this bracket, most of the time probably the line. And it just means that you take dy dx and you evaluate it at that specific value of x. So you just plug in a, so this is really the same thing as writing f prime of a. A function f is differentiable at a if f prime of a exists. Is differentiable in an open interval ab if it is differentiable at every number inside the interval. Let's look at where the function f of x equals absolute value of x is differentiable. So we have to be a little bit careful here. Remember that absolute value of x is a piecewise function, so it has a different rule for positive and negative x values. So let's consider positive x values first. Let's just look at it when x is bigger than 0. Well, then the absolute value of x is equal to x. So if we take the derivative, f prime of x, we get that it's equal to the limit, as h goes to 0, of the absolute value of x plus h, plug that in for f of x plus h, minus f of x, which is absolute value of x, over h. But as we said, x is greater than 0, so that means that this limit just becomes x plus h when we remove the absolute value, and absolute value of x just becomes x. Okay, so that's super nice. X minus x in the numerator cancels and just leaves c with h. So this is the limit of h over h, which is just the limit of 1, which is just 1. Okay, let's look at what happens if x is negative. Well, in that case, the rule for absolute value is that it becomes minus x, because we need, if it's a negative number, then we need another negative to cancel and make sure that the absolute value stays positive. So it becomes minus x, where x is negative, so minus x is positive. Okay, so then our derivative f prime of x is again our limit of absolute value of x plus h minus absolute value of x over h. But in this case, when we get rid of the absolute value, it's a little bit different. It has to be minus x plus h, and it has to be minus a minus x over h. So again, tons of stuff cancels in our numerator. However, instead of being left with h over h, we're left with a minus h over h. So that means it's the limit as h goes to 0 of minus 1, which is minus 1. Okay, we still didn't consider what happens if x equals 0. So let's check out that part. If x equals 0, then our derivative at 0 is equal to the limit of f of 0 plus h. minus f of 0 over h. Okay, so then that's the limit of 0, absolute value of 0 plus h minus absolute value of 0. Okay, so 0 plus h is just h, so it's absolute value of h. Absolute value of 0 is 0, so we can forget about it. And we get that it's the limit of absolute value of h over h. So let's see if we can compute this limit of absolute value of h over h. Well, it's absolute value, so we should probably consider it from the right and from the left so that we can split it up into positive and negative rules for absolute value. So if I look at the limit as h goes to 0 from the right of absolute value of h over h, then that's the limit of h over h, because we're only considering positive values of h. So the absolute value is positive there. Okay, so that's just the limit of 1, which is 1. If I consider the limit as we go from the left of absolute value of h over h, then from the left we're thinking of negative numbers for absolute values, so that's just negative h over h. So from the left we're looking at the limit of minus 1, which is minus 1. Hang on, our limits don't match from the right and from the left. So that means that f prime of 0 does not exist, because this limit does not exist. And the limit was equal to f prime of 0. So it looks like we only have f prime of x defined for positive values and for negative values, but not for 0. So f prime of x is a piecewise function. It's 1 if x is greater than 0. It's minus 1 if x is less than 0. And it does not exist at all at 0. We can see this by looking at the graphs. So this is y equals f of x, which is absolute value of x. Okay, notice if I look at a tangent line to a line, it's literally just a slope of that line. So the derivative all along here is the slope of this line, which is 1. Similarly, the derivative all along here is the slope of the tangent line here, which is just the line itself. So it's slope of minus 1. However, if I were to zoom in over here, notice when I zoom in, no matter how much I zoom in at 0, I never get to a point where I can actually draw a straight line. What we're used to is zooming in on, let's say, part of a curve, let's say over here. The more you zoom in, the closer and closer you get, the more that the curve straightens out and looks like a straight line. So you can actually draw a tangent line. Whereas over here, the more I zoom in, it doesn't make any difference. It still stays just as pointy. I've got limits on the left and limits on the right that don't match. So there's no way that I could possibly even draw. I could draw like a tangent line over here, but I could also draw a tangent line over there. I could draw any number of them. There's too many different ones that don't match. So there's no one specific tangent line. So the derivative does not exist over there at that point. If I look at the derivative for where it does exist, this is y equals f prime of x. Then it's 1 for all positive values of x. And it's minus 1 for all negative values of x. And notice it does not exist at 0. Notice that even though the derivative is not defined at 0, this function absolute value of x actually is continuous at 0, because the limit as x goes to 0 of absolute value of x is equal to 0. And if we let f of x equal absolute value of x, that is the value of the function at 0. So this is an example of a function that is continuous at a point, but not differentiable at a point. So just because a function is continuous does not mean that it's differentiable. However, the reverse actually is true. If a function is differentiable, that does force it to be continuous. So let's do that as a theorem. If f is differentiable at a, then f is continuous at a. If we have, let's say, something like this that is a point, we can see that's an example of a function that is continuous but not differentiable. If we have a function that is, discontinuous, then that function definitely can't be differentiable now, because if f is differentiable, it must have been continuous. So if a function is not continuous, then there's no way that it can be differentiable. That's the contrapositive of this statement. And we also can have a function, let's see if I can draw a little better. We also can have a function fail to be continuous if there is a, there we go, that's the best one. If there is a straight drop, because then a tangent line would be horizontal, which has vertical, and vertical lines have undefined slope. So the derivative as the slope of the tangent line would be undefined. So let's prove this theorem. If f is differentiable at a, then that means that the limit of f of x minus f of a over x minus a as x tends to a exists. In other words, if I look at the limit of f of x minus f of a, then I can be a little clever. I can divide by x minus a and multiply by x minus a. That's the same as multiplying by 1. Then this is the slope of the secant line. So the limit is the derivative. Because f is differentiable at a is what we're assuming that this derivative exists. So that means that this limit is no problem. It exists. It's equal to f prime of a. So I can take the limit of the product by doing the product of the limits. So I do the two limits separately. And then this limit is the derivative. This limit is a polynomial, so I just plug in a for x, and I get a minus a, and it's 0. So that means that this entire limit that we started with is 0. Okay, so let's use that. Let's calculate the limit of f of x as x goes to a. We want this to be equal to f of a in order for f to be continuous. So we, again, are a little bit clever. We like to insert a little more information than we had, so we add f of a and we subtract f of a. That's the same thing as adding 0. Then the limit of the sum is the sum of the limits, so we split that up into the limit of f of a and the limit of f of x minus f of a. But we just computed this right over here, and we saw that it equals 0. So that means that we have the limit of f of a as x goes to a. Well, that's just f of a. There's no x in there. The limit of a constant is a constant. And then this limit is 0. So we get f of a plus 0, which is just f of a. Exactly what we wanted to prove. Okay, so if the derivative f prime of a function f has a derivative of its own, we call it the second derivative of f, and denote it by f prime prime, which we'll call f double prime. So that's d dx of dy dx, which we also write as d squared y dx squared. Okay, so if f of x equals x cubed minus x, let's find and interpret f double prime of x. Okay, by example 2, we already know that the derivative of f is 3x squared minus 1. We calculated that the long way. So that means that we just have to calculate the derivative of that. So f double prime of x is equal to the derivative of f prime, which is equal to the limit, by definition, of f prime of x plus h minus f prime of x over h. Okay, so that's the limit of 3 times x plus h squared instead of 3x squared minus 1 minus 3x squared minus 1 all over h, which is the limit when we expand of 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1. Okay, then we cancel out everything that we can cancel out, and we're left with the limit as h goes to 0 of 6x plus 3h. Now we can plug in h0 because we canceled it, and we just get that this is 6x. So let's interpret f double prime. Well, remember that the derivative is the rate of change. So f double prime is also a rate of change. It's the rate of change of the derivative, so of the slope of f of x. Instead of being the rate of change of f, it's the rate of change of the slope of f. Let's take a look at this on our calculator. We can plug in for y equals, let's see, we have x cubed minus x, oops, and we have f prime is 3x squared minus 1, and then f double prime is 6x. So our original function is blue, our derivative is red, and our second derivative is black. So as we saw before, the red function shows the rate of change of f, but then our black function is the kind of the slope of the slope. So our black function should be negative whenever the red function is going downwards, which it is. You can see that as the red function goes down, the slope of the tangent line is negative. Then it should be 0 all the way at the bottom, because then the tangent line for the red function, the derivative, becomes horizontal. And then it starts going up again. So then my derivative becomes positive. The y values change to positive values. Okay, it should also make sense that this is how it's going to match up with our original function, because if this thing is changing and it's going up, my derivative is positive, my second derivative is negative because it's only the change of the change, which in this case is going down. So we have to be a little bit careful. It can be hard to see the second derivative from the original function, at least with what we know at the moment. We have to look at the derivative to compare it, and then compare that one to our original function. And then we can verify that the first derivative and second derivative that we computed are correct. The instantaneous rate of change of velocity with respect to time is called the acceleration, a of t, of an object. It is the derivative of velocity and is therefore the second derivative of the position. So if position is s, that means that s double prime is acceleration, which is v prime. The third derivative, f triple prime, is the derivative of the second derivative, denoted by f double prime prime, which is f triple prime. The instantaneous rate of change of acceleration with respect to time is called the jerk, j of t, of an object. It is the derivative of the acceleration function and therefore the third derivative of the position function. So j of t is a prime of t is v double prime of t, which is s triple prime of t. Okay, the fourth derivative I don't even know if I'm going to even call this f quadruple prime. Probably just call it the fourth derivative. In general, the nth derivative of f is denoted by this funny little thing where we put f, instead of writing it as an exponent, we put parentheses around it. So those parentheses tell you it's not an exponent. And they tell you it's actually the nth derivative. It is obtained by just differentiating f n times. So that's the same thing as saying dny over dxn. Okay, let's do an example of finding a couple more derivatives. We just found the second derivative for this guy. So let's find the third derivative and the fourth derivative. Well, we already know that the second derivative is 6x. So if we were to graph that, which we did, then we know that y equals 6x is that straight line. So it's a straight line that has slope 6. So m is 6, so that means that it's a straight line, has a tangent line, that's just the line itself. So the slope of the tangent line is also 6. So that means that this derivative of this y equals 6x function must be equal to 6. So it means f triple prime. We don't even have to calculate it. It's, by definition, it's the slope, so it's equal to 6. Okay, if we were to graph that, y equals 6 is a horizontal line. Horizontal lines have slope 0. So if the slope of y equals 6 is 0, that means the slope of any tangent line to y equals 6 is 0, because it's a straight line. So that means that the derivative, which is the slope of the tangent line, so that fourth derivative of the original function, must be 0.